Hi there, this is Dr. Maxwell, and we're going to talk about Chapter 7, where we prove some non-conditional statements. But the first type of statement is actually just the equivalent of two um, conditional statements. So when you're faced with a biconditional proof, you just have to prove the direct statement, which I call P implies Q, and its converse, Q implies P. And here's the outline of the proof. Uh, we're just saying that you might do any of these things. We've looked at many ways to prove a conditional statement now. So we'll do an example. This is homework number 2 in your chapter 7. This says if x is any integer, then x is odd if and only if 3x plus 6 is odd. So I would first write this as two conditional statements. So if x is odd, then 3x plus 6 is odd. And that's my P implies Q. And then for Q implies P, I need to prove if 3x plus 6 is odd, then x is odd. It's a good idea for you to write these things down, but it's not part of the proof. So how does our proof begin? With the word proof. So we're going to establish that x is an integer, and then sometimes I'll say something like this. First, suppose x is odd. And then we'll just see where this takes us. What do we know about odd numbers? Then x equals 2a plus 1 for some a that's an integer. So we're just going to substitute and see where it goes. Substitution yields what? 3 times 2a plus 1 plus 6. All right, that looks like if we multiply this out, we get 6a plus 3 plus 6, which is 6a plus 9. And now I'm just going to rewrite this as 2 times 3a plus 4 plus 1. So you see why I did that? I need to show that 3x plus 6 is odd. So now just let p be the integer 3a plus 4 to see that what? 3x plus 6 equals 2p plus 1, and so 3x plus 6 is odd. So that's the first half of my proof. And now I sometimes start a new paragraph. And from here, the next thing we have to do is prove this one. So a lot of times, a lot of times I will say this. Conversely, or maybe I'll start it for the converse. You can work on your own style. Suppose, there'd be a comma there, suppose 3x plus 6 is odd. Okay, we'll see where this takes us. Then 3x plus 6 equals, I don't want to use any of the same letters, so I'll use 2b plus 1 for some integer b. Now, let's see what happens. Okay, so what do we have? We have 3 times x equals 2b minus 5, which I can rewrite as 2 times b minus 3 plus 1. Let's just double check that. Are these two expressions equal? This would give me 2b minus 6, and then I add 1, that turns it into minus 5. Okay, now, technically, what we have right now is that 3 times some number is odd. Now, we have previously proven that odd times odd equals odd, and odd times even equals even. So I'm not going to reprove that. So I'm going to say, first, note that 3x, well, I guess we need to do this first. Sorry. What are we going to do? We're going to say, let q be the integer b minus 3 to see that what? That 3x equals 2q plus 1 is odd. Also, we know 3 is odd. By previous results, the only way 3x can be odd is if x is also odd. And now we are done. We have proven both directions, and we can conclude our proof. So, what do we do? First, we proved if x is odd, then 3x plus 6 is odd. Then we proved if 3x plus 6 is odd, x is odd. X is odd. Okay. Now, you should read section 7.2. Just good to know. We won't be doing any complicated proofs like they present, but I like what he talks about with that theorem and how those kind of theorems work, because you will encounter those kind of theorems. This is in section 7.2. So look that over, see if you can kind of get what he's trying to show you. The next thing that we talk about is not a conditional statement, it's an existence proof. We want to prove that something exists. Sometimes it's a number, sometimes it's an expression or a set or a function. And what we have to do for an existence proof, we have to come up with an example to show that something exists, or we can prove that something exists without providing an example. So there's two different ways we do this. If we actually come up with the example, that's a constructive proof. If we just show that an example exists without actually providing it, that's called non-constructive. So we'll look at a couple of these. Here's our proposition. There is a rational and an irrational number between these two numbers. So for our proof, we just have to come up with some. So for a rational number, there's infinitely many choices. I just chose one. I said, consider this number. 2.555. Okay, let me take a minute up here. Sometimes when you're trying to do something like this, if you really want to see why there's so many choices, and this is how I teach it in Math 154, just add a zero and then you can see, oh, there's lots of numbers in there. You can add 2 zeros. See all the numbers that are in between those two numbers that look so close together? So this number is in between, but we have to show that it's rational. So we can show that the number is rational by writing it as the ratio of integers. So what does it look like as a ratio of integers? Well, an easy way to do this, there you go. You don't have to simplify it. That's a rational number. It's a ratio of integers. And clearly, be careful about using that word in a proof. Clearly, 2.55 is less than this number, which is in turn less than 2.56. So that part's pretty easy. Now, for an irrational number, I just played around a little bit till I found one that was in between. We have the square root of 5 plus what? This number. Okay, how do I know this is irrational? Well, it's the sum of an irrational number and a rational number, which we showed in chapter 6 is irrational. Oops, I hate that. So it is irrational. The tablet I'm using, when you get to be writing down near the bottom of the page, there's an arrow and it flips the pages around. If you ever wonder what the heck's going on when I'm doing that. So to see that, I'm going to go to a new page. To see that this inequality holds, And I wrote it up a little different on your handout, probably a little better. So if you try to find the decimal approximation of this number, well, you just put it in your good old calculator, and this is 2.55 what? 107. I can stop there. So we actually came up with numbers in between these two numbers. For a rational number, I just picked a decimal form and then showed it was rational. For an irrational number, I played around with my calculator till I found one. I'm sure there's a more systematic approach, but I know I needed to find something roughly equal to 2.5, and that wasn't too hard to do. And we explained why this was rational, and then you can look at its decimal approximation to see where it lies on the number line. So that's a constructive proof. We constructed an example. So next, we'll look at a non-constructive proof that's kind of similar, but it only focuses on the rational numbers. This statement says that there is a rational number between any two distinct rational numbers. So if you have two rational numbers, R and S, and they're not equal to each other, so one of them is going to be less than the other. And the proof works exactly the same way. It doesn't matter which one, so we just pick one and use it. But we need this, and I didn't want to do it inside the proof because it gets too long. So, and this is kind of an interesting one. It seems quite obvious, right? If you have two real numbers and A is less than B, then the average of those two numbers is going to be in between A and B. That's basically what this says. So, but how could we prove it? Well, we know how to start. So first, I'm going to say add B to both sides of this inequality to obtain A plus B is less than 2B, or equivalently, A plus B divided by 2 is less than B. And I'm going to call this 1, this inequality. Then, say next, adding A to both sides of the same inequality. So I need a new page. So we're adding A to both sides of the same inequality yields 2A, this is the inequality, is less than A plus B, or equivalently, A is less than A plus B over 2. And that's my second inequality. So combining 1 and 2, we have A is less than A plus B over 2 is less than B. And we are done. Okay, now we need to tackle this. Okay, proof. So this is going to be non-constructive. We're just going to show one exists. So we're going to start with two rational numbers. And they're not the same number. And I will say, without loss of generality, suppose R is less than S. Now, let T equal R plus S over 2. Now, we've got to show that T is a rational number. Show that this is rational. So what do we know? We know R equals A over B and S equals C over D for some, what? Integers A, B, C, and D. Right? So R plus S over 2 equals A over B plus C over D divided by 2, which equals, if we do the arithmetic, AD plus, AD plus BC all over 2BD. So I will let P be the integer AD plus BC, because I'm trying to show this is a ratio of integers, and let Q be the integer 2BD. So what do we have? We have T equals P over Q, and that is rational. And by the previous proposition, you see, we established that this is between R and S. Right? So there, we have shown that between any two rational numbers, you can always find another rational number. There's a word to describe this: dense. The rational numbers are dense. so are the irrational numbers. In fact, between any two real numbers, you can find both a rational and an irrational number. The real line is dense. And that's some interesting stuff that you get into in your upper level courses. So we're going to take a break here. Maybe you should go review the intermediate value theorem, because that is what we're going to do when we come back.